Hello sir, myself N. Shivakumar. I am from Information Technology branch. Today, Tech Talk, my subject is discrete mathematics structures, and the topic is discrete complex analysis and isoradical graphs. Introduction. Discrete complex analysis on isoradical graphs explores the behavior of complex valued functions of isoradical graphs. Isoradical graphs are graphs where all vertices have same degree. Isoradical graphs are graphs where all vertices have same degree. The study of complex analysis on isoradical graphs has applications in network analysis, image processing and physics. The calculus of complex functions, William Johnson. Finally, we can conclude the introduction is isoradical graphs are graphs where all vertices have the same degree. Basics of isoradical graphs. Isoradical graphs are characterized by having all vertices with the same degree, denoted as D. The degree of a vertex in an isoradical graph is the number of edges incident to that vertex. Isoradical graphs can be regular or irregular depending on whether all vertices have the same degree or not. For example, showing for each pair of graphs show that they are isomorphic by showing that there is a property that is preserved under isomorphism, which one is graph is and the other does not. Here is some options. There is A, B, C and D. Discrete complex analysis. Discrete complex analysis studies complex valued functions on discrete domains such as graphs. In the context of isoradical graphs, discrete complex analysis focuses on understanding the behavior of complex functions defined on the vertices of the graph. Discrete complex analysis provides tools to analyze properties like holomorphicity, singularities, and zeros of functions on isoradical graphs, visualizing complex valued functions z by z square minus 3. In the context of isoradical graph, discrete complex analysis focuses on understanding the behavior of complex functions defined on the vertices of the graph. Isoradical graph, Laplacian. Isoradical graph, Laplacian. The Laplacian matrix of an isoradical graph captures the connectivity and geometry of the graph. The eigenvalues and eigenvectors of the Laplacian matrix play a crucial role in understanding the behavior of complex functions on isoradical graphs. The spectral properties of Laplacian matrix provide insights into the discrete complex analysis of isoradical graphs. Holomorphic functions and isoradical graphs. Holomorphic functions and isoradical graphs. A function if defined on the vertices of an isoradical graph is said to be holomorphic if it satisfies discrete Cauchy-Riemann equations. A function defined on the vertices of an isoradical graph is said to be holomorphic if it satisfies the discrete Cauchy-Riemann equation. The discrete Cauchy-Riemann equations relate the values of f on neighboring vertices and the edges of the graph. The study of holomorphic functions on isoradical graphs involves understanding their analytic properties such as derivatives and integrals. Here is a graph which is a function modulus of z. Singularities on isoradical graphs. Singularities are points where a function is not well defined or behave or behaves unexpectedly. In the context of isoradical graphs, singularities can occur at vertices where the function is not holomorphic. Understanding the behavior of functions near singularities is essential for analyzing their properties on isoradical graphs. Reparameterize the curve below. Here is a isoradical graph which is reparameterized in the picture. Zeros of function on isoradical graphs. Zeros of function on isoradical graphs. Zeros of a function are points where the function evaluates to 0. The study of zero of functions on isoradical graphs is important for understanding the distribution and connectivity of the graph. Zeros of functions on isoradical graphs can have implications in various applications such as graph coloring and network connectivity. Two real root set a and b in the graph, and it is equal to y equal to x square minus 2 is the equation. Applications of discrete complex analysis on isoradical graphs. Discrete complex analysis on isoradical graphs has applications in network analysis, where it helps understand the behavior of complex valued signals on interconnected systems. It is also useful in image processing, where complex analysis technique can be employed to extract valuable information from images represented as isoradical graphs. In physics, discrete complex analysis on isoradical graphs can be used to model and analyze quantum systems with discrete structures. Challenges and future directions. Discrete complex analysis on isoradical graphs is a relatively new field with many open questions and challenges. Developing efficient algorithms and computational techniques for analyzing complex functions on large isoradical graphs is an ongoing research area. The integration of discrete complex analysis with other mathematical frameworks such as graph theory and spectral graph theory holds promise for future advancements in the field. Conclusion. Discrete complex analysis and isoradical graphs provides a powerful framework for understanding the behavior of complex valued functions and isoradical graphs. It has applications in diverse fields including network analysis, image processing and physics. Further research and development in this area have the potential to unlock new insights and applications in various domains. Finally, we have to conclude that visualized complex valued functions have z by z square minus 3 conformal map here. Thank you. Sorry. A brief conclusion about the introduction. Firstly, discrete complex analysis and radical graphs explores the behavior of complex valued function on isoradical. Let's have some brief introduction. Isoradical graphs are graphs where all vertices have the same degree. These are basics. How can we draw a isoradical graphs? And the discrete complex analysis on isoradical graphs. Here is a formula which can be used to find a isoradical graphs z by z square minus 3 when a function f is given. We can here a function f is defined on the vertices of your isoradical graph is said to be a holomorphic if it satisfies the discrete Cauchy-Riemann equation. discrete Cauchy-Riemann equation we have seen in previous slide. These are singularities. Singularities are which is when we studying about isoradical graphs, we have to know about the singularities on isoradical graphs. In conclusion, discrete complex analysis on isoradical graphs provides a powerful framework for understanding the behavior of complex valued functions on isoradical graphs. It has applications in diverse fields including network analysis, image processing, and physics. Further research and development in this area have very potential to unlock new sets and applications in various domains. Thank you.